I'm very pleased to introduce Quadry Chance. Quadry is a sixth-year PhD student at the University of Florida and a graduate of the University of Arizona undergraduate program, astro program here. Quadry studies the occurrence rates of exoplanets around binary star systems. Got his bachelor's from the U of A. He then entered the Fisk Vanderbilt Bridge program in 2018 and moved on to the University of Florida PhD program in 2019, where he works with Professor Sarah Ballard. Since then, he has received a NASA Finest Scholarship Fellowship and a predoctoral research position at the Center for Computational Astrophysics in New York City. Quadry is also a 2022 NASA Exo Explorer, and in his free time, he enjoys wildlife photography, science fiction, and fantasy books, and playing bass in Star and Planets Journal Club, which is a band, not a journal club, which was deeply confusing because there is a journal club at the University of Florida called Star and Planets Journal Club.
There's also a soccer team and a flag football team.
We might want to work on expanding our naming
No, never change.
conventions.
It's hilarious.
Anyway, so with that said, take it away, Kyle.
Great. So I'll be freestyling this talk since I don't have my speaker notes. So feel free if you have any questions to stop me during. We have a pretty small collection of people, so feeling that is fine.
Is your laptop muted?
Yes.
Okay.
I think it's
Oh, okay. Gotcha. Okay.
Great, so we'll get started. So this is a screenshot from the hit video game Hollow Knight, which some of the other students in my research group have been obsessed with. I promise it's relevant. In this game, you play this little guy who goes around like saving the world from evil, like most video games. But something that stuck out to me is that in this game, none of the characters speak. They kind of like burble at you. But there's no sort, as far as the story goes, there's no talking back and forth. All the clues that you get about the world that this person lives in and all the history of it comes from environmental storytelling. You know, the placement of, a statue, some lights, some characters in the background, even without using words, it relays like the depth and character of this video game world. And I like to think that, especially as an exoplanet scientist, that's kind of like what I do. Like, we're learning from things that aren't necessarily right in front of us. We're not being told things, but from various small clues.
Maybe you can see it from here because we have a mic over there and people from Zoom have difficulties here.
Okay.
You can feel free to bring your laptop. Maybe I can check if the mic can be increasingly.
That's like
The mic, I think it's over there on the
Yeah.
ceiling.
the ceiling.
in the ceiling. It's a great place for my.
Okay.
All right, can you hear me now?
Say a little more.
Test 1 2 1 2. Can you hear me now?
Okay, they say that's a little better.
So
Yeah.
just sit here and speak up.
So I guess to sort of try to contextualize where I sit in astronomy, I do this to embarrass my advisor Sarah whenever I'm giving a talk and she's in the room. But when I was born in 1995, that was just after we had found the first exoplanet, sun-like star. And then Sarah's advisor, Dave Charbonneau, was a huge part in the early history of exoplanets, discovering more and more, bringing the numbers up to like tens of exoplanets. Then Sarah graduated from undergrad in 2007. I think I was in like 5th grade or something. I'll share this recording later. But I think her kind of generation of exoplanet astronomer like went from just looking for exoplanets to having so many exoplanets we didn't know what to do with, and therefore being able to actually learn things about the planets themselves, like in a demographic sense, with the Kepler mission. And I'd like to think that my generation of exoplanet astronomers, the 3rd generation, will be learning not only like the demographics of exoplanets, but specific things about planets themselves, especially with JWST. So I guess my PhD has covered like all of the scales in exoplanet astronomy. And the first project I did was looking at the role of giant impacts in planet formation. So this is a plot that if you do exoplanets, you're very familiar with. This is showing the radius distribution of planets and the number of planets orbiting per number of planets per star. You can see there's, with this helpful red arrow, there is a deep valley at about 1.8 Earth radii. We call this the radius valley. It appears to be the result of some combination of a lot of different processes, but the main one being photoevaporation or core powered mass loss. So basically some sort of like hydrodynamic gas escape that pushes planets that are born to one side or another. So these two mechanisms predict the very similar, like the similar feature in a similar place, the radius gap, which makes it pretty hard to tell which one is dominant. But there are some systems where if we assume that either core powered mass loss or photoevaporation is what's happening, the planets don't quite make sense. So here on the right are a bunch of compact multi-planet systems, and with equilibrium on the x-axis and their density on the y-axis. So if you assume that something like photoevaporation is happening, generally your densest planet should be the one closest to the stars. It's experiencing the most evaporation. And you would expect like a kind of monotonic decrease in density should go out and the UV radiation gets less intense. However, as you can see here on this plot, there are some systems that have weird jumps in density. And combining this with the fact that the radius gap that we saw in the last slide isn't as empty as you might expect if only these processes are happening, I think that implies that there's a few more things that work, and one of those things would be giant impacts. So in this project, we're dealing with the fact that we only have like a snapshot of planetary systems. And really the only information that we have about what happened in their past is their current architecture, the current arrangement of planets. So what we generally do is take the planet formation simulations and compare that to, we run our planet formation simulations, compare that to our current population of planets to try to learn what those conditions were like and how that could have affected the planetary systems we see today. And so what I did in this project was looking at giant impact erosion of their atmospheres. And so when you think about that, there are two kind of distinct phenomena that happen. There's the actual atmospheric displacement from the impact shock wave. You can think of it as just like splashing the atmosphere off of the planet. And then now you've deposited all of this thermal energy into the planet, which also enhances atmospheric escape. Here's a plot from Yelenovich and Schlichting showing the size ratio of impactor to impactee and the amount of atmosphere that you would expect to be removed. As you can see, you don't need to have a very large impactor compared to impactee to remove a significant amount of atmosphere. And seeing as this is something that planet formation simulations, like we think that, you know, there is a era of giant impacts when planets are forming naturally. This would be an important thing to learn about as far as what our planet populations look like today. Here's another diagram showing where you inject all this kinetic energy and then you lose a bunch of energy in the wind and a Parker wind, leaving you with a much smaller atmosphere than you started with. So a lot of the work that Sarah's group does includes building like a realistic population of planets, doing and making sure that that population is matches the observed population, doing a thing to it, in my case, that is hitting them with other planets. And then seeing what comes out on the other end of that as far as planet populations. In this case, I use simulations from a previous paper by Rebecca Dawson, in an attempt to sort of like save on both time and like energy, because it takes a non-trivial amount of trees, I guess, like to think of it, to run an in-body simulation. We then have to observe them with like a Kepler like survey to get back basically our Kepler statistics and then compare that to the real Kepler statistics. So in these simulations, what they were looking at in the original Dawson paper was how do you produce single transiting versus multi-transiting systems, so-called Kepler dichotomy. Whereas like single transiting systems are dynamically hotter, so planets are more eccentric, more inclined, and for multi-transiting systems are flat, dynamically cold, usually close together. Yeah, so the dynamically hot systems make up about 90% of systems, and the dynamically cool ones make up about 10% to produce the statistics of planet multiplicity that we see. The other thing we need is like to build actually the model for the giant impacts, because actually doing like a hydro simulation of a giant impact is not really feasible on a scale. Also doing a planet formation simulation, because there are a lot of giant impacts. And so we need to build a model for atmosphere stripping on the same planet population, so I can turn it on and off to see the effect. And I also need a model for photoevaporation. So for the photoevaporation part, I use vPlanet, which is a suite of a lot of different planetary evolution codes. I assume that all planets accrete like 5% of their mass in atmosphere. And then all of them are subjected to the same UV flux of a solar mass star over 5 gigayears. And then planets that lose more than 90% of their envelope are considered to have lost their atmosphere. For giant impacts, the median impact energy is really high when you're looking at late stage planet formation, because you're looking like Moon, Mars size impactors on Earth-ish sized planets. So in kind of hand wavy sense, that's more than enough energy to unbind the whole atmosphere from the planet. And it's much more than you would just expect from the mechanical shock. There's been work since then that indicates that it's more like 80%. But since most planets go through 2 to 3 giant impacts, I think that it doesn't change the conclusions from this work. And so for simplicity's sake, we assume that one impact in this work will remove all of the atmosphere of one of the planets. And so this is kind of like a snapshot of some of those planets. This is one of the first ever plots I made in grad school, and it kind of takes me back to look at it. So here we have all our planets, and these are all the planets that we can see in green. So in the multi system, we tend to see many more planets in the same system. Where in singles, we're just seeing one. Here's what happens when you photoevaporate. All the planets interior to it looks like 50-ish days lose their atmospheres. But when you use giant impacts, the number of the planets that lose their atmospheres change. It's not necessarily the innermost ones. And it happens all over the system, almost regardless of size. I don't know if you can see the difference here. So
When you said singles and multis, are you talking about the stars
no,
or just the planet architecture?
yeah, I'm talking about, is there one transiting planet system or multiple?
Okay.
So there are diverging outcomes here, since you have in one population, one, like, you can pretty well predict which planets are gonna lose their atmosphere, and the other one, it's more stochastic. So there exist populations of planets density wise that don't exist in the other regime. So for giant impacts, when that is what's sculpting the planet atmospheres, you get low density planets that are far from their star, kind of tenuously holding on to atmospheres, and high density remnant cores that would, under photoevaporation, generally be holding on to an atmosphere, but since it's been removed, you have this very high density remnant core. So those are highlighted in the red ovals there. So this is a plot of the density versus the semi-major axis for these remaining planets. And then for photoevaporation, when you get low density kind of high mass planets, because they're inflated, they're very hot, but they're still just holding on their atmospheres. And you get partially photoevaporated cores, which again have a different density than a fully evaporated core. That's less dense. So I think one of the big things that I took away from doing this work was that even though planet formation seems to produce planets of the same size in compact multisystems, have you all heard of the peas in a pod kind of phenomenon? Planets tend to be the same size. If photoevaporation dominates the shape of the radius distribution, what I think it does, then planets shouldn't be kind of misordered in their systems, and there should be very few planets in the radius gap. Here I have a period radius diagram from the simulations, and since this was just kind of like a rough toy model, you can't expect this to reproduce reality, but there's a really wide gap here where planets undergoing photoevaporation avoid, whereas there are quite a few planets in this gap in reality. And so something that could explain that is giant impacts. Giant impacts produce planet cores that are in this gap because, again, they're stochastic. And so, at least in the way I think of it, not all stars are made the same like they were for this paper. So if you have a star that is outputting like relatively little XUV radiation, so it's not aggressively photoevaporating close planets, and one of those planets undergoes a giant impact, well, now you have a planet that ends up in the radius gap. And so I spent a lot of time on this back when I first got to grad school. I looked at a bunch of things that did not end up in the paper, one of which was this, which, like, if there's a giant impact that's happened, there should be a lot of things that indicate that that's what's happening in a planetary system. The most obvious of which is, I think, the eccentricity and inclination of systems where impacts have happened. Like, those planets should look a little wonky because they didn't have like an orderly formation. And that's generally true. So in the left panels here on these two plots, that's for intrinsic singles where the signals sort of washed out, because for these single planets, there's a lot of interaction in between planets. And you've kind of heated all of the planets beyond where you can see the signature of this. But for multis, where you have some giant impacts happening, there's a very clear spike near the radius gap where all of those planets which have gone through a giant impact have both higher eccentricity and inclination. Now, I put this down for like 3 years after this and went to go work on other stuff that I'll talk about in a minute. But earlier this year, man, it seems like forever ago, but I went to extreme solar systems in New Zealand, and I'll be damned if somebody didn't bring up, like, if there is apparently a peak in eccentricities for planets in the radius valley, which is exactly what should happen if giant impacts is what's putting those planets there. I've been like holding my breath for this paper to come out for like 6 months. So with that, we can pause here for any questions on that first part before we get to the second part.
Any questions online?
So after doing that project, or kind of simultaneously, there were a bunch of papers about peas in the pod coming out. So naturally I was interested. And as we just talked about, well, if giant impacts are sculpting at least like a little bit of the planet for planet population, some peas don't look like they belong to the same pod, or they shouldn't. And so here are peas in a pod. Planets look more like their neighbors than they would if this was just a random draw from distribution or radii. I think this is pretty well accepted at this point. There's a lot of contention at the beginning about whether this was just an observational effect, but at least some of it is real. And so I'll bring back this plot. And I'll bring back this whole slide. Like there's naturally some systems that don't follow this trend. And like I know it's like, you have a hammer and everything looks like a nail, but I really think that giant impacts has something to do with this. So I went and looked. This is just a radius distribution plot of all the exoplanet archive system. I know that's bad, so don't jump on it yet. But I'll draw another helpful red arrow. When you look at the radius ratio distribution for all of these planets, for planets that are short of the gap, less than 1.7, that they look like the parent distribution. And for parents above the gap, greater than 1.9 Earth radii, they also look like the parent distribution. But if you look at specifically planets that are in the radius gap or around the radius gap, there is a huge drop in the number of planet pairs that have a radius ratio of 1. So this is saying that if you have a planet in the radius gap, it's very likely to not look like its neighbor.
I'm sorry, what are the different color, in each plot, there's two different colors and I'm very confused.
Sorry. So the purple distribution is the parent distribution and the colored plot is the that particular radius.
Okay, that makes sense, thanks.
So yeah, I guess the first thing I had to do after that was not just go to the Exoplanet archive and download all the radii. So I ended up using the radii from the Travis Berger's 2023 paper, but only using the Kepler ones since those are the most precise radii, and this actually becomes really fuzzy when you're talking about a radius gap, maybe 0.1 Earth radii wide. There aren't a ton of non-Kepler planets that have error bars smaller than that. So this is the group of planets that end up being like in the radius gap within their uncertainties. And so I guess another follow-on from the giant impacts work that if you have a planet of an ambiguous composition or density, and it's coming from giant impacts, that implies that they should also have unusual size ordering and spacing characteristics. And so this is just a plot of the systems of all the planets I just showed you. And you can maybe tell by eye that, this isn't very peas in a pod. The planets, they're not in the right orders. Like you're not going smallest to largest. Sometimes you have really large planets, like really small ones. So something weird is going on with this population of planets. So basically I took that sample of very precise radii planets. There aren't that many of them, so I have to do bootstrapping to sort of make sure that this isn't just like small number statistics. And so here I have a plot of the radius ratio distribution, the outer to the inner planet. In gray is the systems without a planet in the gap. You expect this distribution to peak at 1 if peas in the pod is like the dominant law of the land. In red are systems with a planet in the gap. And black, I guess it's the one you should be paying the most attention to, is like the bootstrap distribution from that. And the blue dotted line is the general size ratio of sub-Neptunes to super Earths Because you could also think, well, if we're looking at things in the radius gap, like we're seeing a big size jump. Maybe that's just going from super Earths to sub-Neptunes. But about half the time it actually goes the other way. Yeah, here in the black distributions, you can see that if we're short of the radius gap by half an Earth radius, get this bump at the the sub-Neptune to super Earth bump. We get the bump at one. Oops, we get the bump at one that we expect. But there's no other kind of weirdness here. It looks mostly like the parent distribution. We look at things that are above the radius gap by 0.5 Earth radii. We get the peak at one and kind of just trails off. But if we look at specifically things that are in the radius gap, we get this dip right at one. So yeah, I guess I think this is like pretty good smoking gun evidence that like there is something going on between planets in the radius gap and their neighbors, and especially considering the fact that planets in the radius gap have higher eccentricities, I think that implies that there's some dynamical reason for this. And my favorite explanation is giant impacts.
So, quick thing, for the middle one, both the peaks seem to shift to the left. And is that just because you might have maybe expected the planets to be, for the ones that it's one, shift to the left because you have a smaller planet now where you're supposed to have a bigger one? Because you've lost the impact? I'm just wondering why it seems that both have shifted left.
Not really sure. Could you see that? That's interesting.
Yeah, because if you look at the smaller planets, you have the peak at one and you have the peak at the sub-Neptune to super Earth. If you look at the right one, you have the peak, the really large peak at one, and then kind of a little bit of a flat line, but you don't see anything there. But in the middle one, you have the peak at greater than one, and you have the peak at less than one. And so I'm just wondering, is that because those are the sub-Neptunes and super Earths that you would expect to see, but the ratio is now different because your planet that you're checking this on is different size than you would expect because it's in the gap and lost something or gained something or whatever?
Yeah, that's an interesting question. I was wondering if like there should be some characteristic size that you're expecting if you had a giant impact, but that is like a far future project, I think.
Thank you.
So I also looked at the period ratios because it occurred to me that, well, the spacing is different, the period ratio should be different. So in gray here again is like the parent distribution, and in black is our distribution of interest. So when we're short of the radius gap, it looks just like the parent distribution. When we're long of it, again, looks just like the parent distribution. But there are very few planets in the sample, so like I don't want to say anything definitive, but I don't think that the middle black distribution looks anything like the gray one. Seems to be an excess of planets at like the 3:2 period ratio. There seems to be a huge excess of planets at integer period ratios, which is like sort of the opposite of what we should expect. And I think that makes some sort of dynamical sense. Especially because like if you're increasing the eccentricity of planets that are close to these, or increased eccentricity makes it easier to get captured into these period commensurabilities. That's not like that's not a scientific thought yet, but I think this is another line of inquiry that's making me think that giant impacts is actually the answer here. Like we need some sort of dynamical thing happening. So yeah, I'm in the middle of trying to submit that paper by the end of this month before postdoc applications are due. Does anybody have any questions about that before we move on to the third thing?
How many planets are actually in that gap sample? And it's very small, right? It's
like 38.
I'd say tens, yeah.
Yeah. Yeah, the main obstacle is just that test isn't precise enough to actually like precisely locate planets in or out of the gap. Although I think like once you get enough planets, it probably shouldn't matter.
Yeah. How many of them have masses?
I think like a third of them. So it's not enough of them to be useful. Yeah.
So this is, unlike part one of the talk, this is observational data pretty much entirely. Right? So we don't have the luxury of running simulation for a few years. But is it possible that this distribution of period ratios is odd? Not because the planets were kicked to a new permanent weird period ratio, but because they haven't actually settled into a new stable orbit yet. Is there if that's a possibility, would there be a way to test that?
Yes, one of my group members, she works on stellar ages. And we talked about this a few weeks ago. At least the planets in the gap sample, they seem to be of like Kepler star age, but that's like, 4 plus or minus 2 billion years. So I don't know, I guess would be the best answer. Like, there's nothing glaring, like they're not like way younger than the other planets are. So we'll move on to the third part. This consumed most of grad school for me. I'm interested in how binary stars affect the planetary system that we see, considering that most stars are in binaries, and even if most of those don't host planets, it makes binaries have a lot to do with what we see in planets. And so there's been so much work looking at the sort of like suppression effect of binaries, looking at circumbinary planets. The most relevant thing to me here is the suppression effect, there where when you start bringing stars closer to 1,000 AU to like hundreds of AU, the occurrence rate of planets starts to go down. And thus far, that's been kind of limited by the fact that we're having to do these sort of like find out which stars are binaries through adaptive optics. And like once you get to like Kepler distances, it's like kind of hard to do. And so I guess the first step in this project is I need to be able to determine which binary to binaries, particularly if I want to learn about close binaries, like within 50 AU. It's a non-trivial exercise. I want to draw attention to the fact that like this idea and the previous idea of like what's kind of like the radius distribution of planets telling you about what's happening to them, those ideas are linked. This is work from Kendall Sullivan. I think they are at UCSC right now, but they've done painstaking work with the sample of Kepler adaptive optics targets planets to see that the radius distribution for planets that are in binaries, even wide-ish binaries, a few hundred AU, the radius distribution is different than that of other planets. Like the mechanism for this, I think, is not exactly clear, but there's something here. So what I did for 4 years of my life was work on how to find unresolved binaries with Gaia. Oh, that sucks. Okay, that'll work. So most people will look for binaries with Gaia using astrometry, but I'm using the RV instrument on Gaia. And so here is just a plot of radial velocity where one star has companion and one star doesn't have companion. And so Gaia takes RV measurements, not randomly, but sparsely. And so you might have 5, 10, 20, 25. Not a lot of stars have more than 25 measurements over the course of when Gaia was launched to whenever DR3 came out. And so it can be kind of hard, especially when they don't give you the individual measurements. All you get is like the median RV and then some uncertainty on that. But from that, you can tell which star has a companion, because the one that has a companion has a really large uncertainty. And so if you think of it like there's some distribution of RV noise that where some of it's intrinsic to the star and some of it is created by a companion. And you assume that stars are like mostly the same if they're in the same color and magnitude, like sky position, like they should mostly look the same to our instruments. And therefore they should have similar RV error bars. Basically, if you identify the stars that are in the tail of that RV error distribution, you can make a pretty good guess at the fact that there is some binary companion. So here's what that ends up looking like. So in orange is just the singles and blue is just the binaries. And if you just identify things that are way out in that tail, well, that's almost all binaries. And so doing this isn't as trivial as I made it sound, because you need to understand the per transit, so the per measurement uncertainty from Gaia, and they don't just give that to you. You have to estimate it. Whoops. And so this is basically a plot of that. Me and Dan Foreman Mackey spent a lot of time working on this, but by color and magnitude, you can actually figure out what the RV uncertainty is. And it's actually like surprisingly good when you start getting toward brighter targets. So being able to use that, and we can just simulate a bunch of binaries, give them colors and magnitudes, and then just kind of see what we get back. And this is basically a plot of that and separation and mass ratio. So you can see, so these contours are like the 99% detection rate contours. So even for things that are like 11, 12th magnitude, you can go down to mass ratios of like 1 to 100, which is a brown dwarf in a lot of cases. We lose out on completeness up here toward the left because Gaia culls things that have RV errors that are too high, like more than 40 kilometers a second. But beyond that, like we should be able to detect basically like every eclipsing binary, for example. And here are some planet relevant binaries. We do detect Kepler-16 and several of the other circumbinary planet hosts as binary stars. So here's another plot of like our completeness for our completeness and how that changes with the measurement uncertainty and semi-amplitude. So I think the left plot here is most important. Basically anything that's a star orbiting another star within like 10-ish AU should be detected. And that's kind of what I wanted for the study, because that's the sort of area where we have the least amount of information on binaries and planet formation. And so people have done like really similar things with astrometry. Here's a color magnitude diagram from Quadry. I have no idea how to read. But you can see that they have a lot of coverage of the bottom part of the main sequence. And I don't know, this was sort of like an inspiration to be able to like do this for many more stars than they were able to do it. I guess slides are up. Just talk about this. So here is an unnamed group of stars, and what our pipeline gives you is called paired, is a probability of it being a single star. So this is just a distribution of its probabilities for a population of stars. And here is the distribution of probability of being a single star for another population of stars. Now, without any sort of like going and looking at a light curve or going and getting radial velocity measurements, like with a big telescope, you can tell that the blue population is the just Kepler, the kick, and the orange population is just the Kepler EBs. So well over 70% of them are in the zero bin, meaning that we can pretty accurately recover most ecliptic binaries. This is a measurement from Gaia using their non-single star catalog with spectroscopic, like single line spectroscopic binaries. That's in green. The black would be like if what we were seeing was Gaussian always only. Red is kind of where we place the conservative cutoff we would consider a binary. And you can see that like 90% of things in the SB1 catalog are detected as binaries. More than that if we're less conservative. This is the equivalent of that figure that I showed you before. And I think this looks right as far as like all of the structures you expect to see in a color magnitude diagram with binaries. And I think the best part about this tool is that, well, it's like just on GitHub, we put it on GitHub, and you can sort of just forward model like what any population of binaries should end up looking like to Gaia. So that's kind of what we did here is a test. Like I injected a bunch of binaries to see if we could pull out what their semi amplitude was. And for the most part, we can. Things over here, if the per transit measurement uncertainty is too large, then it's kind of a crapshoot. But for most of the things that we have a p-value for, whether or not we think it's a binary, we can also give some value for what we think the semi-amplitude of that binary is, which I think is really cool. So DR3 has a similar measure for about 6 million stars. This is a huge stumbling block in the referee process of this paper because I submitted it like a date after DR3 came out, and then the referee was like, why did you do this? But they can do this for about 6 million stars, and we can do it for about 30 million. And at least for the population of stars where they have a semi-amplitude for, our semi-amplitude seem to line right up with theirs, which is encouraging for the other 24 million stars. And we also seem to match it really well with ground-based data. So this is from the SB9 catalog, which combines a lot of different RV measurements for binary stars. And while the agreement is a little bit less tight than with Gaia itself, I think that this is a really encouraging sign that like, wow, this actually works.
Did you filter SB9 for just in plain saying binaries at the transit, or does that include everything at all
It
inclinations?
includes everything.
So you expect some noise there. Yeah.
So yeah, most what I want to use this for is we know about this binary suppression effect. So how deep does it go? Like what chain is it as you get the binaries closer and closer? That's kind of like a lot more complicated than I thought it was going to be originally. But this at least is a preliminary plot. And purple is just the distribution of our p-values for the kick. And in green is the distribution for the KOIs. And there seems to be a lot of separation between the two, which should be the case because stars that host close binaries should be significantly less likely to host planets. The specifics of that are probably going to have to wait a year or two, but I'm really encouraged by this plot. And that's all I got for you. Any questions? I'm the most excited. Like I've talked about this project a lot, so maybe it doesn't sound like that, but I'm the most excited about paired, like because a lot of people from outside of exoplanets have been using it. for whatever star people do. And I'm really excited about the fact that, wow, like something I made like is really useful to people.
Could you send me the GitHub link for Aaron and I will send it out later. Are there any questions in the room? More questions in the room? And are there any questions from our online attendees for Quadry? You can either raise your hand or you can shout. So for paired, you said your sort of outer separation limit is about 10 AU or
Charitably, for bright stars, it's like around 10 AU. Call it 5 if it's not too bright.
but the mass ratio of the two stars is about 1 to 100. So we'll go down to brown dwarfs, but not spurious detections of.
For the brightest stars, you can't like, for the brightest stars and the heaviest Jupiters, you can detect them, but whether something that's like 7 Jupiter masses, the planet or a brown dwarf is.
Yeah, I mean, this is really, really cool. So I mean, I think you mentioned this, but I'm curious, like, did you look at kind of relatedly, like the combining the RV, you know, filtering off of like, say, like RUI filtering, looking, you know, at the astrometric error for binary is like how much of the parameter space ends up being kind of completed, like if you combine both approaches.
It depends on magnitude. If you combine both, and obviously like the inclination of the system. If you combine both at the bright end, they're like touching, but if you get towards the dim end, they separate again. I guess one thing I should say, like this is effectively RUI, but for RV
Yeah.
measurements.
Yeah, that's really, like, I briefly started looking into this at some point, but I got lost. I'm very excited to see you looking at it. I also, when I was looking at it, I noticed, and I don't know if you can really like do it like the same sort of like modeling that you're doing with this, but also a correlation, and you mentioned this with the high error of like Gaia targets within the like temperature range of normally having RVs, not having RVs was also sometimes indicative of there being a binary, like if it's an SB2 and it breaks on the fitting or something. Did you look at all at like tagging that in as well?
No, since we don't get the RVs from it, it just kind of
Yeah,
gets dropped from that. Now, hopefully that'll change in later data releases.
Last call for questions, in the room or online. Someone online just have a comment? Oh, that was you. I'm now suspicious of the microphone, so. All right, well, thank you very much, Quadry, for an excellent talk.